Hello everyone, this is Mel. Today we're gonna go through Chapter 3 summary of VC Specialist Math Unit 1 and 2. Okay, so Chapter 3 is about sequence and series. We're gonna go through arithmetic sequence and series and geometric sequence and series, and a little bit of the application and recurrence relation of this form. Okay. So the first dot point says the nth term of a sequence is denoted by Tn. So the first term will be T1 and second term T2 until Tn, the nth term. Okay, so this forms a sequence. And the second one, a recurrence relation. So what is a recurrence relation? It enables each subsequent term to be found from previous term. So a sequence specified in this way is said to be recursively. For example, if we have Tn equal to Tn minus 1 plus 2. So this example shows a recursive sequence or a recurrence relation. So the next term can be defined by the previous term. For example, if we have the previous term as n minus 1 over here, then the next term will be get from this relation. So this is the previous one, then plus 2. So these are how the previous and the subsequent term to be related. And this defines a recursive sequence. Okay, other than the recursive sequence, we can have the sequence can be defined not on the previous term, but on the n. So if we have T2, then it should be equal to 2 times 2 minus 1, which is 3. So instead of being defined by the previous term, it's defined by the n. Okay, this is another way to define a sequence. Okay, let's move on to arithmetic sequence and series. An arithmetic sequence has a rule of the form like this. So it consists the first part, A, which is the first term. So A is actually T1. And n minus 1 times D. This D is the common difference. So we have D equal to Tk minus Tk minus 1. So Tk is the subsequent term and Tk minus 1 is the previous term. So if we have a sequence like this, so the odd sequence, 1, 3, 5, 7, 9, the D should be the difference between any two terms. For example, 9 and 7. So the D should be 9 minus 7, which is 2. Or you can take 5 and 7, for example. 7 minus 5 is also 2. So it does not matter which pair you take. You just need the pair next to each other. So Tk and Tk minus 1. Or Tk plus 1 minus Tk for all k greater than 1. Okay, this is an arithmetic sequence. The sum of the terms in an arithmetic sequence is called arithmetic series, so the sum. So we add all the terms together to get the series. The sum of the first n terms of an arithmetic sequence is given by the following. So this formula over here, or it might be easier to look at this one. So A, we already said, is the first term, and L is the last term, Tn. So we plus, for example, we still use this one, 1, 3, 5, 7, 9. We want to find S5, which is the sum of the first 5 terms, and that's equal to 5 on 2. The first term is 1 and the last term is 9. 25. And that's how we find the series. So in general, arithmetic sequence tells you we have the first term, then we plus the difference, get the second term, plus it again, get the third one, and the fourth one, and the fifth one, and so on and so forth. And the series tells us we want the sum of all these. So what's 1 plus 3 plus 5 plus 7 plus 9? And using this formula, or this one, is basically the same. We get the sum, which is equal to 25. So series is about the sum, and the sequence is about a sequence of numbers. Okay, the geometric sequence and series. So what is geometric sequence? A geometric sequence has a rule of the form Tn equal to A, which is also the first term. So it's A equal to T1, and times R. So what is R? R, instead of the D, the common difference, we have now the common ratio, which is the division between Tk and Tk minus 1, or you can say Tk plus 1 divided by Tk for all k greater than 1. Okay, so for example, if we have A equal to 1, so T1 is 1, and R equal to, let's say, 2. So we multiply by 2 every time to get the next term. So how do we find the common ratio for this sequence, for this geometric sequence? We can do the difference between 8 and 4, the division, which is 2, or any other pair next to each other. Okay? And the formula is Tn equal to the first term times the common ratio with the power of n minus 1. We can actually verify that using this geometric sequence. For example, let's have T3, which is 4, and it's also equal to the first term, 1, times by the R, which is 2, with 3 minus 1 as a power. So that's 2 to the power of 2, which is 4. So yeah, that's true. Okay, the next dot point, the sum of the terms in a geometric sequence is called series, geometric series. The next one, for R does not equal to 1, the sum of the first n terms can be given by this, or this one. So I prefer to use this one because this is just a special case for R greater than -1 and smaller than 1. Even if, and this one is R for all real number not equal to 1. Okay? So I prefer to use this one. You don't need to remember this one. Okay, that's the formula for the geometric series for the sum. Let's do an example still using this sequence. Let's do S4. So the sum of the first 4 terms, which is equal to A is 1, R is 2, power is 4, minus 1, R is 2 minus 1, which is 2 to the power of 4 minus 1, which is 15. And it should be equal to 1 plus 2 plus 4 plus 8 equal to 15. So that's correct. The next dot point So for r greater than -1 and smaller than 1, the sum as n approaches a limiting value as n approach to infinity, and the series is said to be convergent. The limit is called the sum to infinity and is given by this formula. So we can think of it as a square. So for r equal to half, which is between -1 and 1, let's say if the first term, a is equal to 1, then what's as infinity? It should be 1 over 1 minus half, which is 2. And we can actually represent this using a square. For example, the area of the square is 1, which represents the initial a. And after we multiply the r, we get half, and then a quarter, and then 1/8, 1/16. So every time we run it through r, so we get half. So initial is all the area, then we get half, then another half, another half, another half, and till it approaches to 0. So this actually tells us if the sequence have Tn is approaching to 0, that means this series is said to be convergent, and the sum is also convergent to a single number. Okay, let's move on to application of geometric sequence. So the first one about compound interest, the second one about depreciation. So one is plus and the other is minus. So how's that? Suppose that we have $P is invested at an interest rate R per annum. Compound annually, then the value of the investment after n years is AN, and it's given by this, which is similar to our geometric sequence. And the R is 1 plus R divided by 100. So how do we actually understand the compound interest? So it actually means when the interest is earned on both the original amount and the accumulated interest. So every year we have an interest, and the next year the interest is on both the previous year and the previous year's interest. So we can conclude it as interest on interest. And about depreciation. So instead of the plus sign, we have the minus sign here, which actually means when an asset lost a fixed percentage of its value each period. So each year it lost 5%, and the next year on that 5% lost another 5%. And that's about depreciation. For the recurrence relation of the form Tn equal to R times Tn minus 1 plus D. So it's actually like a combination of the arithmetic, where you do have a plus D, and the geometric, where you do have a R times Tn minus 1. So it's a combination of geometric and arithmetic sequence. Or you can think of it this way. So if D is equal to 0, then you have Tn is equal to R times D minus 1, which is just a geometric sequence. And if you have R equal to 1, which Tn is equal to Tn minus 1 plus D, which is just a arithmetic sequence. Okay, so it's a combination. So if we have T1, 2, 3, and be a sequence defined by the recurrence relation of the form, where R and D are constant, the nth term of the sequence can be determined by the first term, T1, the R, and the D. Okay? And this form can be written in the form of A plus A times R n minus 1 plus B. So A is this part, and B is this part, the whole part. Okay, so a very common example is when they ask you to, let's say if we have a recurrence relationship with Tn equal to 1.05, Tn minus 1 plus 500. So this is like a finance question where R is interest or depreciation factor and D is a regular deposit or withdrawal constant. And this part represents the interest. So if we have 5% of the interest, then we do R plus 5/100, which is just 1.05. Okay, this can also be applied to a population model where R is the growth factors and D is the, for example, fixed migration per year. So if you have plus how many people, migration per year, and R is the growth factor. Okay, that's it for today. Thanks for listening. This is Chapter 3 summary, sequence and series.